Tonight, our journey does not take us to the distant stars or the edge of time. Instead, we travel backwards, deep into our own planet's history, to a world that is both alien and intimately familiar. It is a world shrouded in mist, dominated by vast silent forests, and ruled by creatures that defy our modern sensibilities. It is a world where dragonflies the size of eagles soared through the air, and millipedes as long as cars crawled across the forest floor. This is the forgotten world of giant insects. Before the first dinosaurs walked the earth, before the first flowers bloomed, there was an age when arthropods, the ancestors of today's insects, spiders and crustaceans, were the undisputed kings of the land. This was a time when the very air was different, when the planet's climate nurtured a kind of gigantism we can now only imagine. Join us as we step back into this lost chapter of Earth's story. We will breathe the air of this ancient world, walk beneath its colossal fern trees, and come face to face with the silent armoured giants that once dominated the planet. This is not a story of monsters, but a story of life's incredible ability to adapt and thrive in conditions utterly different from our own. It is a calm, meditative exploration of a world that was, a quiet contemplation of the forces that create and ultimately reclaim even the most formidable of life forms. Our story begins approximately 359 million years ago, in a geological period known as the Carboniferous. The name itself, derived from the Latin for coal-bearing, hints at the defining feature of this age. This was a time of immense planet-spanning forests, unlike any that exist today. The world was a vast, humid greenhouse, a kingdom of green and brown shrouded in a perpetual warm mist. To truly understand the giants that lived in this world, we must first understand the world itself. The continents were not arranged as they are today. They were coalescing into a single supercontinent known as Pangaea. Vast stretches of land were low-lying and swampy, covered by shallow, brackish seas. The climate was hot and humid year-round, with little to no seasonal variation. There were no great ice caps at the poles. The entire planet was a temperate or tropical zone. But the most crucial difference, the key that unlocks the secret of the giant insects, was in the very air they breathed. During the Carboniferous period, global oxygen levels were not the 21% we are accustomed to today. Due to the explosive proliferation of plant life and a unique set of geological circumstances, the atmosphere was superoxygenated. For millions of years, the oxygen content of the air soared to as high as 35%. Imagine breathing this air. It would have been thick, heavy, and incredibly rich. For life, this abundance of oxygen was like a potent fuel, supercharging metabolisms and allowing for biological possibilities that seem fantastical to us now. The forests of the Carboniferous were a silent, alien landscape. There were no flowers, no fruits, no birds singing in the canopy, and no mammals rustling in the undergrowth. The dominant plants were giant club mosses, like lepidodendron, which grew in dense, straight columns over 100 feet into the sky, their bark covered in a diamond-like pattern of leaf scars. There were colossal horsetails like calamites, forming dense thickets of bamboo-like stalks. And there were vast forests of giant tree ferns, their enormous fronds creating a deep, dark canopy that sunlight struggled to penetrate. When these giant plants died, they fell into the stagnant, oxygen-poor water of the swamps. In our world, dead organic matter is quickly broken down by fungi and bacteria. But in the Carboniferous, the types of microbes that could efficiently decompose lignin, the tough woody tissue of plants, had not yet evolved. So, the dead trees did not rot. Instead, they piled up, layer upon layer, over millions of years. This immense accumulation of buried plant matter was slowly compressed and cooked by geological pressure and heat, eventually transforming into the vast coal seams that power our modern world. Every piece of coal we burn is a fossilized remnant of these ancient silent forests, a piece of the Carboniferous sun stored for 300 million years. This unique combination of factors, a hot, humid climate, vast swampy forests, and an atmosphere saturated with oxygen, created the perfect cradle for a new kind of giant to emerge. The land was a buffet of plant matter and decaying detritus, and the air was rich with the fuel needed to power large, active bodies. The stage was set, and onto this stage crawled the true rulers of the Carboniferous world, the the giant arthropods. They were the pioneers of this green kingdom, the first great dynasty to conquer the land, and their size would be unmatched by their kind ever again. As we immerse ourselves deeper into the misty, oxygen-rich atmosphere of the Carboniferous, our attention is drawn from the colossal silent trees to the air itself. This was not an empty sky. It was a domain, a kingdom ruled by the flutter and hum of wings on an unimaginable scale. And the undisputed sovereign of this aerial realm was a creature that embodies both the beauty and the alien nature of this forgotten world, Meganeura. The name itself means large-nerved, a reference to the intricate network of veins on its fossilized wings, but a more evocative name would simply be the giant dragonfly. Yet, to call it a dragonfly is an understatement. This was not the delicate, shimmering insect we see darting over ponds today. Meganeura was a predator of terrifying proportions. With a wingspan that could reach up to 75 centimeters, or 2.5 feet, it was the size of a modern-day eagle or a large hawk. It was, and remains, the largest known flying insect of all time. Imagine standing in that ancient swamp forest. The air is thick, warm and heavy with the scent of damp, earth and decaying vegetation. The only sounds are the gentle drip of water from giant fern fronds and the whisper of the wind through the scale-bark trees. And then you see it. A shadow passes overhead, swift and silent. It is not a bird, for birds have not yet evolved. It is Meganeura. Its 2 pairs of vast, glassy wings beating with formidable power, carrying its long, armoured body through the dense air. Its enormous, multifaceted, compound eyes, each composed of thousands of individual lenses, would have given it a near 360-degree field of vision, making it an exceptionally skilled hunter. Like modern dragonflies, Meganeura was a master of flight. Its 2 pairs of wings could beat independently, allowing for incredible agility. It could hover motionless in the thick air, pivot in an instant, and accelerate to high speeds in pursuit of prey. Its 6 legs, bristling with sharp spines, were not used for walking, but were held forward in flight, forming a catching basket to snatch unsuspecting victims from the air or from the branches of trees. And what did this aerial titan hunt? Its prey would have consisted of other large arthropods. The Carboniferous air was filled with a variety of flying insects, some quite large by our standards, and Meganeura was the apex predator of this ecosystem. It would have hunted other primitive flying insects, and perhaps even ventured to snatch small amphibians or early reptiles from the ground. Its powerful, serrated mandibles were perfectly adapted for gripping and tearing apart its prey mid-flight. The sight of a Meganeura hunt would have been a swift, silent, and brutal display of aerial dominance. The secret to Meganeura's immense size lies directly in the superoxygenated atmosphere we have discussed. Insects do not have lungs like we do. They breathe through a network of tiny tubes called tracheae that run throughout their bodies, delivering oxygen directly to their cells. In today's atmosphere, with 21% oxygen, the efficiency of this system limits the maximum size an insect can attain. The oxygen simply cannot diffuse deep enough into the body to supply the tissues of a very large insect. But in the 35% oxygen of the Carboniferous, this limitation was lifted. The high partial pressure of oxygen meant that it could diffuse much further and more efficiently through the tracheal system. This hyperoxygenation supercharged their metabolism and allowed their bodies to grow to sizes that seem monstrous to us today. Meganeura was not a freak of nature. It was the logical and beautiful result of an insect body plan being allowed to reach its full potential in an environment perfectly suited for it. The life cycle of a Meganeura would have been similar to that of a modern dragonfly, but on a much grander scale. It would have begun its life as a nymph, an aquatic predator living in the stagnant, swampy waters. These nymphs would have been formidable hunters in their own right, perhaps several inches, long preying on fish, primitive amphibians and other aquatic invertebrates. After spending a period of its life in the water, the nymph would have crawled out onto a plant stem for its final molt. It would have shed its larval skin one last time, and from the husk of the aquatic hunter would have emerged the magnificent winged adult, the king of the Carboniferous skies. For millions of years, Meganeura and its relatives, the griffinflies, patrolled these ancient forests. They were a testament to the success of the arthropod body plan. They were the first creatures to truly conquer the air on a grand scale, long before the pterosaurs and birds would take flight. Their silent, glassy-winged reign represents a unique and unrepeatable chapter in the history of life on Earth. As we stand in quiet contemplation of this magnificent creature, we are reminded that the world we know is not the only world that has been. The laws of physics and biology are constant, but the environment is not. And when the environment changes, it opens up new possibilities, allowing life to explore forms and sizes that, to us, belong only in the realm of myth and legend. Meganeura was not a myth. It was a living, breathing reality, a calm, colossal predator soaring through the forgotten, oxygen-rich skies of a world long past. As the giant griffin flies patrol the skies above, our journey takes us down to the forest floor into the deep, damp and dimly lit world beneath the canopy of colossal ferns and scale trees. The ground here is a thick, springy carpet of decaying plant matter, mosses and fungi. The air is still, heavy, and filled with the earthy scent of decomposition. It is a world of shadows and silence, but it is far from empty. Here, in the gloom of the undergrowth, lived the undisputed terrestrial titan of the Carboniferous, a creature so immense and alien that its fossilized remains have inspired both awe and disbelief for over a century: Arthropleura. The name Arthropleura means jointed ribs, a fitting description for a creature that was, in essence, a colossal armoured centipede or millipede. But to compare it to its modern relatives is to fail to grasp its sheer scale. The largest millipedes today might reach a length of 30 centimetres, or about a foot. Arthropleura, however, grew to staggering proportions. Based on fossilised tracks and body segments, scientists estimate that it could reach a length of up to 2.5 metres, or over 8 feet, and a width of nearly half a metre. It was as long as a small car and as wide as a man's torso. It was, by a huge margin, the largest terrestrial invertebrate that has ever lived. Imagine the sight: a rustling in the giant ferns, a disturbance in the thick carpet of leaf litter, and then, emerging from the shadows, is Arthropleura. Its long, flattened body, composed of approximately 30 jointed segments, moves with a slow, inexorable, wave-like motion. Each segment is protected by a thick armoured plate, forming a formidable shield of chitinous armour. Dozens of pairs of legs, perhaps as many as 30 or 40, propel its immense body forward, their rhythmic movement carrying it silently over the forest floor. Its head, small in proportion to its body, would have been equipped with a pair of antennae, constantly sensing the environment, tasting the chemical signals in the air and soil. For many years, Arthropleura was envisioned as a fearsome predator, a giant carnivorous centipede hunting down large amphibians and early reptiles in the Carboniferous swamps. This was a terrifying, but perhaps inaccurate, picture. More recent evidence suggests a gentler nature. The discovery of fossilized gut contents and the structure of its mouth parts point towards a diet primarily composed of plant matter. It seems Arthropleura was not a predator, but a mega-herbivore, or more accurately, a detritivore. It was a giant, mobile decomposer, a terrestrial earthworm on a colossal scale. It would have spent its days and nights slowly crawling through the rich, decaying vegetation of the forest floor, consuming vast quantities of rotting plant material, spores, and fallen seeds. In doing so, it played a crucial role in the Carboniferous ecosystem. It was a vital nutrient cycler, breaking down the tough plant matter that other organisms could not, and returning those nutrients to the soil, helping to sustain the very forest that fed it. It was not a monster, but a giant armoured gardener, a key component in the planet's first great terrestrial ecosystem. Like Meganeura, Arthropleura's gigantism was made possible by the hyperoxygenated atmosphere. While it likely possessed a tracheal system similar to modern insects, its immense size and flattened body shape may have also allowed it to absorb some oxygen directly through its cuticle, particularly at the joints between its armoured plates. The high oxygen levels would have fueled the immense metabolic demands of its large body, allowing it to grow to a size that would be impossible for any land-dwelling arthropod today. Its sheer size would have also been its primary defence. In a world without large vertebrate predators, a fully grown Arthropleura would have been virtually invulnerable, its thick armour protecting it from any smaller creatures that might have viewed it as a potential meal. The fossil record of Arthropleura is fascinatingly incomplete. We have found numerous body segments and, most impressively, long fossilised trackways. These tracks, found in ancient sandstone deposits in places like Scotland and North America, look like parallel sets of tiny footprints, forming a trail as wide as a tire track. They are the fossilized footprints of these giants, a tangible record of their passage across a landscape 300 million years ago. Standing beside one of these trackways, you can almost feel the presence of the immense creature that made it, a silent testament to a lost world. What we have never found, however, is a complete, fossilized head. This lack of a complete skull is what has made determining its exact diet so challenging for paleontologists. The life of an Arthropleura would have been one of slow, steady growth. It would have hatched from an egg as a much smaller version of itself and grown larger with each successive molt. The process of molting, shedding its rigid exoskeleton to grow a new larger one, would have been the most vulnerable time in its life. A freshly molted Arthropleura, its new skin still soft, would have had to hide away in the undergrowth, waiting for its armour to harden, protecting it once more. As we contemplate this calm, colossal crawler, we are looking at a different model of success. It was not a swift predator like Meganeura, but a slow, steady and essential part of its environment. It represents a path that life on land could have taken, a world where invertebrates, not vertebrates, were the dominant large animals. For millions of years, Arthropleura was the king of the Carboniferous forest floor, a silent armoured giant that witnessed a world of perpetual twilight beneath a canopy of alien trees. Its existence is a profound reminder that the history of life is filled with incredible experiments, magnificent forms that rose, dominated their world for a time, and then vanished, leaving behind only faint tracks in the sands of time. Our journey through the Carboniferous world now leads us away from the solid ground and into the murky, stagnant waters that defined this era. The vast, swampy forests were threaded with a labyrinth of shallow seas, brackish lagoons, and slow-moving rivers. These aquatic realms were not peaceful sanctuaries. They were dark, mysterious, and teeming with life, including some of the most formidable predators of the age. Here, in the oxygen-poor waters, a different kind of giant thrived, one that harked back to an even more ancient marine ancestry, the giant sea scorpion, Pulmonoscorpius. The name Pulmonoscorpius means breathing scorpion, a name given because scientists initially believed it was one of the first scorpions to be fully adapted to life on land. However, its physiology suggests it was, at the very least, semi-aquatic, spending much of its life in or near water, and it was a creature of nightmarish proportions. While modern scorpions might fit in the palm of your hand, Pulmonoscorpius could reach a length of up to 70 centimetres, or nearly 2.5 feet. It was a true monster of the Paleozoic swamps. Imagine this creature emerging from the dark water at dusk. Its segmented body is covered in a tough, dark exoskeleton. It possesses 8 legs for walking, 2 large, powerful pincers, chelae, at the front for seizing prey, and a long arched tail tipped with a fearsome stinger, likely capable of injecting a potent venom. Its eyes, adapted for low-light conditions, would have made it an effective hunter in the murky depths or during the twilight hours. Unlike the herbivorous, Arthropleura Pulmonoscorpius was an active and aggressive predator. It would have occupied a high position in the food chain of the Carboniferous wetlands. Its diet likely consisted of other large arthropods, fish, and, most significantly, the early 4-limbed vertebrates, the amphibians, that were just beginning to make their mark on the world. A large amphibian, perhaps a metre long, resting at the water's edge, would have been a prime target for this giant scorpion. The attack would have been swift and brutal, the powerful pincers gripping the victim, while the venomous tail arched over to deliver a fatal sting. The existence of such a large terrestrial predator, even a semi-aquatic one, raises questions about its respiration. While the high oxygen levels of the Carboniferous were certainly a factor, the respiratory system of a scorpion, which includes structures called book lungs, is different from the tracheal system of insects. It's possible that Pulmonoscorpius's immense size was not just a product of high oxygen, but also a relic of its ancestors. Scorpions belong to the Chelicerates, a group that includes spiders and horseshoe crabs, and their ancestors, the Eurypterids or sea scorpions, were the apex predators of the Silurian and Devonian seas, some growing to even larger sizes than Arthropleura. Pulmonoscorpius may have been one of the last gasps of this ancient dynasty of giant aquatic arthropods, adapting its ancestral gigantism to the new opportunities of the Carboniferous swamps. But the giant scorpion was not the only terror in these waters. The Carboniferous was also known as the Age of Amphibians. While arthropods ruled the land and air, vertebrates were beginning their own experiments with terrestrial life. The amphibians of this period were not the small, timid frogs and salamanders we know today. Many were large, formidable predators, perfectly adapted to the swampy environment. Creatures like Proterogyrannus were a prime example. Reaching lengths of over 2 meters, it had a long, powerful body, a flattened tail for swimming, and short, sturdy legs. It looked like a cross between a giant salamander and a crocodile. Its skull was large and filled with long, sharp, conical teeth, indicating a diet of fish and smaller amphibians. It was an ambush predator, lurking just beneath the surface of the water, its eyes poking out, waiting for unsuspecting prey to swim by. It was a powerful swimmer, but its well-developed legs suggest it was also capable of moving on land, perhaps to travel between pools of water, or to bask on the muddy banks. The relationship between these giant amphibians and the giant arthropods would have been a complex one of predator and prey. A large Proterogyrannus might have preyed on a smaller Pulmonoscorpius, while a fully grown Pulmonoscorpius could have easily taken down a juvenile amphibian. It was a world of brutal competition, where the first great dynasties of land-dwelling vertebrates and the reigning kings of the invertebrate world clashed in the dark and silent waters. This aquatic ecosystem provides a crucial context for the world of giant insects. It shows us that the gigantism of the Carboniferous was not limited to the land dwellers. The entire biosphere was operating on a different scale. The abundance of food, the warm climate, and the unique atmospheric conditions created a perfect storm for evolutionary experimentation. Life was exploring the upper limits of size in multiple lineages simultaneously. As we peer into these murky primeval waters, we get a sense of a world in transition. The ancient reign of the giant aquatic arthropods was giving way, but their terrestrial cousins were at their zenith. At the same time, our own distant ancestors, the vertebrates, were taking their first, tentative but ultimately world-changing steps. The swamps of the Carboniferous were a crucible of evolution, a place of conflict and competition that would shape the future of life on Earth. The silent armoured giants that lurked in these waters were not just monsters of a forgotten age. They were key players in the story of our own origins, the gatekeepers that our distant relatives had to overcome to eventually inherit the Earth. For tens of millions of years, the world of giant arthropods thrived. The warm, humid, oxygen-rich environment of the Carboniferous period was a seemingly eternal paradise, a perfect cradle for the immense dragonflies that ruled the skies and the colossal crawlers that dominated the forest floor. Meganeura, Arthropleura, and Pulmonoscorpius were the undisputed masters of their domains, the magnificent products of a unique and stable global climate. But the story of our planet is a story of relentless and often dramatic change. No paradise lasts forever. The very conditions that allowed these giants to flourish were destined to unravel, leading to the slow, inexorable decline and ultimate extinction of their entire world. The end of this era was not brought about by a sudden, cataclysmic event like an asteroid impact, but by a slow, grinding and global transformation of the climate, a period that scientists sometimes refer to as the Carboniferous rainforest collapse. The beginning of the end started around 305 million years ago, as the Carboniferous period began to transition into the Permian period. The primary engine of this change was a combination of geology and climate feedback loops. The slow but unstoppable dance of plate tectonics was continuing to push the Earth's land masses together. The supercontinent of Pangaea was nearing its final assembly. As vast continents collided and merged, massive mountain ranges like the precursors to the Appalachians were thrust upwards. This had two profound consequences. Firstly, the formation of a single colossal landmass dramatically altered global weather patterns. The interior of Pangaea became incredibly arid and dry. The moisture-laden winds from the ocean could no longer penetrate deep into the continent's heartland, which became a vast desert. The planet's climate began to shift from a uniform, global greenhouse to a world of extremes, with hot, dry interiors and more seasonal variations. Secondly, the uplift of mountain ranges and the changing sea levels began to drain the vast, shallow swamps that had dominated the Carboniferous landscape. The low-lying wetlands that had served as the cradle for the giant ferns and scale trees began to shrink, fragment and disappear, replaced by drier, more elevated terrain. The great coal forests, the very foundation of the entire ecosystem, were beginning to die. This geological transformation triggered a critical change in the Earth's atmosphere. The Carboniferous forests had been the planet's lungs, pumping out enormous quantities of oxygen. At the same time, the unique burial of dead plant matter, which became coal, prevented that carbon from being released back into the atmosphere through decomposition. This process, known as carbon sequestration, was a one-way street. Carbon was being taken out of the atmosphere and buried, while oxygen was being released. This is what drove oxygen levels up to their incredible peak of 35%. But as the forests began to shrink and the climate became drier, this process slowed down and then reversed. With fewer trees, less oxygen was being produced. The drier conditions also meant that dead plant matter was more likely to decompose or be consumed by wildfires, releasing its stored carbon back into the atmosphere as carbon dioxide. The great carbon burial machine of the Carboniferous ground to a halt. Slowly, over millions of years, the atmospheric composition began to shift. Oxygen levels started a long, steady decline, falling from their peak of 35% down towards the more familiar levels of Earth's later history, eventually settling near 21%. For the giant arthropods, this was a death sentence, delivered in slow motion. Their entire existence, their very gigantism, was predicated on the hyperoxygenated atmosphere. The tracheal system that had so efficiently delivered oxygen to the tissues of a 2.5-foot dragonfly was no longer adequate in an atmosphere with 30%, then 25% oxygen. The laws of physics, which had once been their greatest ally, now turned against them. The decline would have been gradual, almost imperceptible from one generation to the next. Each successive generation of Meganeura would have found it just a little harder to fly, their massive flight muscles struggling to get enough oxygen to power their enormous wings. They would have become slower, less agile predators. Over thousands of years, natural selection would have relentlessly favoured smaller and smaller body sizes. A smaller body required less oxygen and could be more efficiently supplied by the tracheal system. The magnificent giants of the sky were being systematically downsized by an invisible atmospheric force. The same fate befell Arthropleura. The colossal millipede, which may have relied on absorbing some oxygen through its skin, would have found its metabolic needs impossible to meet as oxygen levels plummeted. Its immense body, once a fortress of invulnerability, became a metabolic prison. Only smaller individuals with a more favourable surface area to volume ratio could survive. The changing climate also brought new competitors. The drier, more seasonal world of the Permian period was much better suited to the newly evolving vertebrates. While the amphibians were tied to the disappearing swamps, a new group was on the rise, the reptiles. With their scaly, waterproof skin and their amniotic eggs that could be laid on dry land, reptiles were perfectly adapted to conquer the arid interior of Pangaea. They were no longer dependent on the water. As the giant arthropods were shrinking and struggling, the reptiles were diversifying and growing. Creatures like Dimetrodon, a large sail-backed predator, became the new apex predators of the landscape. A shrinking, struggling Meganeura, or a juvenile Arthropleura, which would have had no natural enemies in the Carboniferous, now became a potential meal for these larger, more efficient and more intelligent vertebrate hunters. The ecological niches that the giant arthropods had once dominated were now being taken over by a new dynasty. The world of the Permian was a harsh, alien place for the survivors of the Carboniferous. The vast, humid forests were replaced by hardy conifers and seed ferns. The air was thinner, and the competition was fiercer. The era of the giant insects was over. They did not vanish overnight. For millions of years they clung on, their descendants becoming progressively smaller, adapting to a world that no longer favoured their gigantism. The lineage of the griffinflies survived well into the Permian, but they were shadows of their former selves, their wingspans measured in inches, not feet. Arthropleura disappeared from the fossil record entirely, leaving behind only its fossilized tracks as a memory of its colossal reign. The extinction of this forgotten world is a profound and poignant story. It teaches us about the deep and intricate connection between life and the planetary environment. The giant insects were not evolutionary failures. They were a spectacular success, perfectly adapted to a specific set of environmental conditions. When those conditions changed, they were unable to adapt quickly enough, and the very traits that had made them successful, their immense size and their reliance on high oxygen, became their downfall. As we contemplate the end of this era, we are left with a sense of calm melancholy. We see a world of magnificent alien beauty fade away, replaced by a new world, one that would eventually lead to the dinosaurs and much later to us. The story of the Carboniferous rainforest collapse is a powerful reminder that our planet is a dynamic, ever-changing system. The conditions we take for granted, the composition of our air, the stability of our climate, are not permanent. Life adapts, evolves, and sometimes entire worlds are lost and forgotten, buried like the great coal forests, waiting to be rediscovered. The silence that fell over the world of giant insects was the silence of a chapter closing, making way for the next, equally incredible story in the epic of life on Earth. Our journey through the mists of the Carboniferous is now complete. We have walked beneath the canopy of colossal trees, witnessed the silent flight of eagle-sized dragonflies, and stood in awe of car-sized crawlers. We have seen the rise of a world utterly alien to our own, and we have traced the slow, inexorable forces that led to its demise. Now, as we return to our own time, we are left to contemplate the echoes of this lost world. What is the legacy of these forgotten giants? What lessons can we, the inheritors of a vastly different Earth, draw from their magnificent and tragic story? The tale of the giant insects is more than just a fascinating chapter in a paleontological textbook. It is a profound meditation on the nature of life, the fragility of worlds, and our own place within the grand, unfolding narrative of this planet. The first and most powerful lesson is one of contingency. The world we inhabit, with its familiar ecosystems, its 21% oxygen atmosphere, and its vertebrate-dominated fauna, feels inevitable, almost preordained. But the story of the Carboniferous giants shatters this illusion. It reveals that the history of life is not a straight line leading inexorably to us. It is a branching, unpredictable path, filled with incredible experiments and alternative possibilities. For 50 million years, the planet belonged to the arthropods, in a way it never has since. They were the kings of the land and air. Their world was not a primitive, underdeveloped stage waiting for more advanced creatures to take over. It was a mature, stable, and spectacularly successful ecosystem in its own right. If the geological and atmospheric conditions of the Carboniferous had persisted, who is to say what might have evolved? Could intelligence have arisen from an invertebrate lineage? Could a civilization of social insects have built cities of chitin and mud beneath the giant ferns? These questions are unanswerable, of course, but they serve a crucial purpose. They force us to recognize the profound contingency of our own existence. We're here not because of some grand design, but because of a series of cosmic and geological accidents, the specific composition of our atmosphere, the particular history of continental drift, the timely extinction of the dinosaurs. The world of giant insects is a stark reminder that what is not the same as what had to be. It instills a sense of humility, a recognition that our own world is just one possible outcome among countless others. The second lesson is a deep appreciation for the interconnectedness of life and the planet. The story of the giant insects is not just a story about biology, it is a story about geology, chemistry, and atmospheric science. The rise of these giants was not an isolated evolutionary event, it was a direct consequence of a planetary scale system. The evolution of lignin in plants led to the formation of coal, which led to the sequestration of carbon, which led to the rise of atmospheric oxygen, which in turn allowed for the evolution of giant arthropods. It is a breathtakingly intricate chain of cause and effect, a perfect example of how the biosphere and the geosphere are locked in a deep, symbiotic dance. This interconnectedness also works in reverse, as shown by their extinction. A change in plate tectonics led to a change in climate, which led to the collapse of the forests, which led to a drop in oxygen, which led to the downfall of the giants. This teaches us that no ecosystem, no matter how stable it may seem, is isolated from the larger planetary system. The health of the living world is inextricably tied to the health of the non-living world, the air, the water, the rocks. The giants did not die because they were weak or unfit. They died because the world that had created them was taken away. Their story is a cautionary tale, written 300 million years ago, about the profound consequences of altering a planet's fundamental atmospheric and climatic systems. This leads us to the third and perhaps most relevant lesson, the concept of planetary boundaries. The Carboniferous world was a high-oxygen world, and the life within it adapted perfectly to that boundary condition. When the boundary shifted, that life could no longer be sustained. Our world today has its own set of boundary conditions. Our civilizations, our agriculture, and our very biology are adapted to a stable Holocene climate and a 21% oxygen atmosphere. The story of the Carboniferous giants serves as a natural experiment, a case study from deep time that illustrates the fragility of such conditions. We are currently engaged in our own, albeit much faster, experiment of altering the planet's atmosphere. By burning the fossilized remains of the Carboniferous forests, we are releasing vast quantities of that buried carbon back into the atmosphere, reversing the very process that led to the high oxygen levels of that ancient world. We are pushing the planet's climate system outside the stable boundaries of the Holocene. The story of the Carboniferous rainforest collapse, a climate change event that occurred over millions of years, provides a somber perspective on our own, human-accelerated changes. It reminds us that the Earth's systems are complex and can reach tipping points, leading to state shifts that can fundamentally reorder the biosphere. The world that emerges on the other side of such a shift may be a very different one, and it may not be as hospitable to the life forms, including us, that were adapted to the old world. Finally, the story of the forgotten giants leaves us with a profound sense of wonder and the sublime. It expands our imagination and enriches our understanding of what is possible for life. The knowledge that our planet once hosted dragonflies the size of eagles and millipedes, the size of cars, adds a layer of mythic grandeur to the history of Earth. It transforms the deep past from a dry collection of facts into a living, breathing world of awe-inspiring strangeness and beauty. These creatures were not monsters. They were magnificent expressions of life's creative potential. They were pioneers that conquered new realms and dominated their world for a period longer than humanity has existed. Their silence today is not the silence of failure, but the quiet, dignified silence of a world that has passed into memory. As we look at a piece of coal, we can now see it not just as a source of fuel, but as a fossilized piece of a lost world, a tangible link to the misty, giant forests of the Carboniferous. When we see a dragonfly darting over a pond, we can see in its shimmering wings a faint, distant echo of its colossal ancestors that once ruled the ancient skies. The forgotten world of giant insects is a story that stays with you. It is a calm, deep, and resonant tale that speaks of the immense and beautiful complexity of our planet's history. It teaches us humility in the face of deep time, respect for the intricate web of life, and caution about our own impact on the planetary system. It is a story that reminds us that we are just one chapter in an epic that is far older and far grander than we can ever fully comprehend, and that the Earth itself is the ultimate keeper of stories, holding within its rocks and fossils countless other forgotten worlds, waiting for us to listen. Our scientific journey into the Carboniferous has revealed a world that is factual, a history written in stone and coal. But the idea of giant insects has haunted the human imagination for far longer than we have known about Arthropleura or Meganeura. Long before paleontologists unearthed the first fossilized wing, giant insects crawled and flew through our myths, our nightmares, and our stories. This deep-seated fascination and fear reveals something profound about our own psychology and our relationship with the natural world. This chapter is a journey not into the past, but into the landscape of the human mind, to explore why the concept of giant arthropods holds such a powerful and enduring grip on us. From ancient folklore to modern cinema, the giant insect has been a recurring motif, almost always portrayed as a monster. In Japanese mythology, the omikade is a terrifying mountain-sized centipede that preys on dragons. In Greek myths, Arachne is transformed into a spider, a symbol of horrifying otherness. This archetype taps into a deep primal fear. Insects are, for many, the embodiment of the other. Their alien anatomy, with their exoskeletons, multiple limbs, and unblinking compound eyes, is fundamentally different from our own vertebrate body plan. They do not have faces we can read or emotions we can understand. They are like biological machines, driven by instincts we find inscrutable. When we magnify this otherness to a gigantic scale, it becomes the stuff of nightmares. A normal-sized spider in the corner of a room can be unsettling. A spider the size of a house becomes a primal threat. A small ant is a symbol of industry. A colony of giant ants becomes an invading army that threatens to overwhelm civilization, as seen in classic science fiction films like Them. This genre, which flourished in the atomic age of the 1950s, used giant insects as a powerful metaphor for our anxieties. The giant bug movies were rarely about the bugs themselves. They were about the Cold War, the fear of nuclear radiation causing monstrous mutations, and the terror of an unstoppable, unthinking enemy. The giant insect became a symbol of nature turning against us, of our own technology creating horrors beyond our control. The discovery of the actual prehistoric giant insects adds a fascinating layer to this psychological landscape. It tells us that our deepest fears were, at one point in Earth's history, a reality. Our nightmares once walked the Earth. This realization is both thrilling and deeply humbling. It validates the power of our imagination, showing that the monsters we conjure are not always pure fantasy, but can be echoes of a real, biological past. The fossil of Meganeura is, in a sense, more terrifying than any fictional monster, because it was real. It required no nuclear radiation, no magical curse. It was a product of the planet's natural processes. This reality also forces us to confront our own sense of scale and dominance. As humans, we're accustomed to being the largest and most intelligent creatures in our immediate environment. The idea of an insect that is larger than us is a fundamental inversion of the natural order as we know it. It challenges our position at the top of the food chain. An encounter with a living Arthropleura would not be like seeing an elephant or a whale. It would be an encounter with something so profoundly alien and so physically imposing that it would force us to question our own biological significance. It would be a confrontation with a different kind of life, a different model of success, one that has existed on this planet for far longer than we have. In more recent science fiction, the portrayal of giant insects has become more nuanced. They are not always just mindless monsters. Sometimes they are depicted as intelligent, hive-mind civilizations, as in Robert Heinlein's Starship Troopers or Orson Scott Card's Ender's Game. In these stories, the bugs represent a form of collective consciousness, a society where the individual is subordinate to the whole. This reflects a different kind of anxiety, the fear of losing our individuality, of being absorbed into a faceless collective entity. It explores the ultimate other, not just in form but in thought and society. Even in more positive portrayals, like in Hayao Miyazaki's Nausicaa of the Valley of the Wind, the giant insects, the Ohmu, are depicted as powerful ancient beings who are the guardians of a polluted world. They are terrifying, but also majestic and essential to the planet's health. They are not evil, but are driven by a deep ecological purpose that humans fail to understand. This perspective aligns more closely with the scientific reality of creatures like Arthropleura, the giant decomposer. It suggests that our fear of these creatures stems from our own ignorance and our destructive relationship with the natural world. The story of the real giant insects, therefore, enriches our fictional nightmares. It grounds them in a tangible past and provides a deeper context for our enduring fascination. It tells us that the world is capable of producing forms of life far stranger and more magnificent than we might believe. The calm, silent giants of the Carboniferous were not monsters. They were simply life, operating under a different set of rules, in a different world. Our continued obsession with them in our stories is perhaps a way for our collective consciousness to grapple with the immense and often terrifying scope of deep time. It is a way to personify the alien nature of our own planet's history. The giant insect is a visitor from a forgotten age, a ghost from a lost world that continues to crawl through the dark forests of the human imagination, reminding us that we are not the only story this planet has to tell. The world of the Carboniferous giants, the eagle-sized dragonflies and car-sized crawlers, seems impossibly distant, a lost chapter separated from us by an almost unimaginable gulf of 300 million years. The Great Drying, the fall of oxygen, and the rise of the reptiles ensured that their specific dynasty came to an end. The planet moved on, and the unique conditions that allowed for their gigantism vanished forever. But does this mean their entire legacy was erased? Is there nothing left of this magnificent invertebrate kingdom in the world we see today? The answer, woven into the fabric of modern biology, is a resounding no. The giants are gone, but their echoes, their distant cousins, and in some cases creatures that are remarkably unchanged, still walk, fly, and swim among us. These are the living fossils, the resilient survivors that connect our time to theirs. To find the most direct descendants of the Carboniferous giants, we must first look not at the insects, but at their more ancient arthropod relatives. The colossal Arthropleura, the king of the forest floor, belong to a group of myriapods whose direct lineage has long since gone extinct. However, its smaller, more humble cousins, the millipedes and centipedes, continue to thrive. When we see a common garden, millipede with its segmented body and wave-like motion of its many legs, we are seeing a miniature living blueprint of the great Arthropleura. The fundamental body plan, the armoured segments, the numerous legs, the role as a decomposer, has proven to be an incredibly successful and enduring design. The millipedes of today are a testament to the resilience of this ancient lineage. They survived the Permian extinction, the age of dinosaurs, and the asteroid impact that wiped them out. They have persisted quietly and efficiently by surrendering the gigantism of their ancestors and embracing a smaller, more adaptable form. Similarly, the terrifying Pulmonoscorpius has its modern counterparts in the scorpions we find in deserts and forests across the globe. The scorpion body plan is one of the oldest and most successful among terrestrial animals. It has remained remarkably unchanged for over 400 million years. The powerful pincers, the segmented tail with its venomous stinger, and the predatory lifestyle are all features that were perfected long before the Carboniferous. A modern scorpion is, in many ways, a miniature version of its giant ancestor. It occupies a similar ecological niche as a nocturnal predator, though on a vastly different scale. The survival of the scorpions is a story of conservatism. Their design was so effective from the beginning that it has required little modification over the eons. They are true living fossils carrying the genetic legacy of the Paleozoic era's aquatic terrors into the modern world. Perhaps the most evocative living link to the Carboniferous skies is the modern dragonfly. While Meganeura and its griffinfly relatives belong to an extinct order, the Protodonata, the true dragonflies and damselflies, the Odonata, flew alongside them. They were the smaller, more agile contemporaries of the giants, and while the giants perished when the oxygen levels fell, the smaller dragonflies survived. The modern dragonfly is a marvel of aerodynamic engineering, a living relic of the planet's first great aerial ecosystem. When we watch a dragonfly today, with its 2 pairs of independently beating wings, its incredible agility, its spiny legs held forward to form a catching basket, and its huge compound eyes, we are witnessing the very same predatory adaptations that made Meganeura the apex predator of its time. The hunting strategy, the flight mechanics, and the fundamental anatomy have been preserved across 300 million years of evolutionary history. The modern dragonfly is a direct window into the Carboniferous skies. It is a smaller, more refined version of its giant cousins, a successful design that was able to weather the storm of atmospheric change by virtue of its more modest size. Every time a dragonfly darts past, it is a fleeting, shimmering ghost of Meganeura, a reminder of the time when its kind ruled the air. Beyond these direct cousins, the Carboniferous world left a more subtle, but equally profound, legacy. The insects themselves as a group underwent a major diversification during this period. The evolution of flight, which we saw perfected in Meganeura, was a revolutionary innovation that opened up a vast new range of ecological possibilities. The ancestors of many modern insect groups, such as cockroaches and mayflies, can be traced back to this period. The cockroaches of the Carboniferous were remarkably similar to the ones we know today, another example of an incredibly successful and resilient body plan. They were generalist decomposers, scuttling through the leaf litter of the ancient forests much as they do now. Their adaptability and hardy nature have allowed them to survive multiple mass extinctions and persist as one of the planet's great survivors. The Carboniferous also gave rise to another crucial evolutionary innovation, metamorphosis. The life cycle of Meganeura, with its aquatic nymph stage and its flying adult stage, is an early form of this strategy. This division of life into 2 distinct phases allows a single organism to exploit 2 completely different environments and food sources, reducing competition between the young and the adults. This strategy was so successful that it was later perfected in the complete metamorphosis we see in beetles, butterflies, and flies, which have a larva, pupa, and adult stage. This evolutionary invention, with its roots in the Carboniferous, is one of the primary reasons for the incredible diversity and success of insects in the modern world. Insects today represent over 80% of all known animal life on Earth, and their global dominance is a legacy that began in the misty giant forests of the Carboniferous. Finally, the most tangible and impactful legacy of the Carboniferous world is, as its name suggests, the coal itself. The vast silent forests, by failing to decompose, locked away hundreds of millions of years' worth of atmospheric carbon. This act of planetary-scale carbon sequestration not only superoxygenated the atmosphere to create the world of giants, but it also kept the global climate in a relatively stable state for eons. The Industrial Revolution and our entire modern civilization was built by unlocking the energy of these fossilized forests. In a very real sense, we are powered by the Carboniferous sun. The electricity that lights our homes, the industries that build our cities, all run on the energy captured by giant ferns and scale trees 300 million years ago. This legacy is a profound and double-edged sword. It has given us the power to build a global civilization, but in releasing this ancient carbon back into the atmosphere at an unprecedented rate, we are unwinding the very process that created that world. We are systematically dismantling the legacy of the Carboniferous, with consequences for our own climate that are becoming increasingly apparent. The story of the giants and their world is therefore not confined to the deep past. It is all around, us. It is in the dragonfly that flits across a pond, in the millipede that crawls in the soil, in the cockroach that survives in our cities, and in the very energy that powers our society. The forgotten world is not truly forgotten. It is simply hidden, its echoes resonating in the biology of its survivors and in the geology of the planet itself. By learning to see these connections, we can develop a deeper appreciation for the immense, unbroken tapestry of life's history, a story that connects the smallest modern insect to the most magnificent giants of the past, and ultimately connects that ancient world to our own. Our long journey back in time is now at its end. We have walked through the spectral forests of the Carboniferous, felt the humid, oxygen-rich air on our skin, and stood in the shadow of giants. We have witnessed a world that belonged not to us, not to mammals, not even to the dinosaurs, but to the vast and silent dynasty of the arthropods. We have seen their magnificent reign and traced the slow, inexorable planetary changes that brought about their downfall. We have found their echoes in the living creatures of our own time and in the very fuel that powers our civilization. Now, all that is left is to stand in the quiet of the present moment and reflect on the meaning of this 300 million year old silence. What does this forgotten world truly say to us across the immense abyss of deep time? The story of the giant insects is, above all, a profound lesson in perspective. In our fast-paced, human-centric world, our sense of time is often limited to our own lifespan, or perhaps a few generations of recorded history. The past is a museum, the future an abstract concept. But the Carboniferous world forces us to confront the reality of deep time. It asks us to imagine a timescale so vast that entire mountain ranges can rise and fall, continents can drift across the globe, and the very composition of the air we breathe can change. To contemplate the 300 million years that separate us from Meganeura is a deeply humbling exercise. It is a span of time more than 1,000,000 times longer than the entire history of Homo sapiens. In the face of such immensity, our own concerns, our triumphs and our failures can seem small and fleeting. This is not meant to induce a sense of meaninglessness, but rather to cultivate a sense of profound calm and liberation. It frees us from the tyranny of the immediate and connects us to a narrative that is far grander and more ancient than our own. It teaches us that we are part of a continuum, a long, unbroken story of life on a dynamic planet. We are not the beginning of the story, nor are we the end. We are simply one chapter, one moment of awareness in an epic of unimaginable length. This perspective also changes our relationship with the non-human world. We are conditioned to see ourselves as the pinnacle of evolution, the planet's ultimate success story. But the world of giant insects presents us with a different model of success. For 50 million years, the most complex and dominant life forms on land were invertebrates. They were not primitive or less evolved. They were perfectly adapted, highly successful masters of their environment. Arthropleura, in its own way, was as much a pinnacle of evolution as the blue whale or the elephant is today. It was the ultimate expression of what an arthropod body plan could achieve under a specific set of environmental conditions. This realization fosters a deeper respect for all forms of life. It challenges our inherent vertebrate bias and encourages us to see the beauty and success in other evolutionary strategies. The intricate design of a dragonfly's wing, the resilient armor of a millipede, the complex social structure of an ant colony. These are not lesser forms of life, but alternative forms of genius, honed by hundreds of millions of years of evolution. The giants of the Carboniferous are the ultimate ambassadors for this perspective. They command our respect not through fear, but through their sheer magnificence and the scale of their success. They remind us that the tree of life is not a ladder leading up to humanity, but a vast branching bush with countless, equally beautiful and valid expressions of existence. Furthermore, the story of their rise and fall is a powerful allegory for the delicate balance between opportunity and limitation. The very factor that enabled their gigantism, the high oxygen atmosphere, was also their greatest vulnerability. They were specialists, perfectly tuned to a world that they could not have known was temporary. When the world changed, their specialization became a fatal flaw. This is a recurring theme in the history of life. Great success in one environment often leads to great vulnerability when that environment shifts. The dinosaurs were masters of the Mesozoic world, but they were unable to survive the sudden, dramatic changes brought on by an asteroid impact. This ancient story resonates with our modern human condition. Our own global civilization is, in many ways, a specialist. We are exquisitely adapted to, and dependent on, a stable global climate and the abundant, cheap energy provided by fossil fuels, the very legacy of the Carboniferous world. We have leveraged this unique set of conditions to achieve unprecedented success, building a complex, interconnected global society. But, like the giants of the past, our greatest strength may also be our greatest vulnerability. Our dependence on these specific conditions makes us fragile in the face of planetary change. The silence of the Carboniferous giants whispers a cautionary tale across the ages. The mightiest empires, whether biological or technological, can be brought down by a shift in the fundamental rules of the planetary game. Finally, the journey into this forgotten world is an act of re-enchantment. In an age where much of the natural world has been mapped, measured, and demystified, it is easy to feel that the age of wonder is over. But paleontology, the science of deep time, pushes back against this notion. It reveals that our planet is a library of forgotten worlds, a place of near-infinite strangeness and wonder. The knowledge that a creature like Arthropleura was not a fantasy, but a real animal that crawled upon this very earth, re-enchants our understanding of the planet. It infuses the ground beneath our feet with a sense of history and mystery. It tells us that the world is older, stranger, and more magical than we can perceive in our everyday lives. This act of discovery is a profoundly calming and hopeful one. It is a collaboration between the patient, silent earth and the curious, pattern-seeking human mind. The earth holds the stories, locked away in its layers of rock, and we, through the patient work of science, learn to read that rock, to translate its silent language, and to bring these lost worlds back to life in our imagination. Every fossil discovered is a word deciphered, another sentence added to the planet's autobiography, and so our meditation on the forgotten world of giant insects comes to a close. We leave this ancient landscape not with a sense of fear, but with a sense of awe and a deeper understanding. The giants are gone, their world turned to stone and coal. A silence of 300 million years separates us from their time. But it is not an empty silence. It is a silence filled with meaning, with lessons, and with a profound, calming beauty. It is the silence of a completed chapter in a story that is still being written, and by listening to that silence we learn to better appreciate the sound and fury of our own brief, precious, and wondrous moment in the sun. Having understood the atomic key that unlocked the potential for gigantism, we must now ascend to the next scale, that of the organism itself. The story of the giant insects is not just a story of a changing atmosphere. It is a story of a unique and ancient body plan, a biological architecture fundamentally different from our own. To comprehend why the Carboniferous world was dominated by giant arthropods and not giant vertebrates, we must first appreciate the elegant yet profoundly constraining engineering of the arthropod body. It is a design that for hundreds of millions of years was a blueprint for smallness, until a temporary change in the world's operating system allowed it to become a blueprint for giants. The defining feature of an arthropod, be it an insect, a spider, a crustacean, or a millipede, is its exoskeleton. Unlike vertebrates, which have an external skeleton of bone, arthropods wear their skeleton on the outside. This external skeleton, or cuticle, is a multi-layered structure made primarily of a tough, flexible polysaccharide called chitin, often reinforced with proteins and, in the case of crustaceans, calcium carbonate. This suit of armour is a marvel of biological engineering. It provides a rigid framework for muscle attachment, offers protection against predators and physical damage, and prevents the organism from drying out. It is one of the primary reasons for the immense success of arthropods, allowing them to conquer every habitat on Earth. However, this external skeleton comes with a significant trade-off, a fundamental engineering problem that directly relates to size, the problem of growth. An exoskeleton is rigid. It cannot grow with the animal. Therefore, in order to get bigger, an arthropod must periodically shed its old skeleton and grow a new, larger one. This process is called ecdysis, or molting. It is the most vulnerable and perilous time in an arthropod's life. The creature must first reabsorb some of the minerals from its old cuticle. Then it must secrete a new, soft and wrinkled cuticle beneath the old one. It then takes in air or water to swell its body, splitting the old exoskeleton along predetermined lines of weakness. Finally, it must painstakingly extract itself from its old shell, a process that can take hours. Once free, the arthropod is a soft, pale and helpless version of itself. It must then pump itself up to its new, larger size and wait, sometimes for days, for its new cuticle to harden and darken. During this period, it is utterly defenseless against predators and the elements. This process of molting becomes exponentially more difficult and dangerous as an animal gets larger. The sheer weight of a large, soft body can be difficult to support against gravity. The surface area available for the new skeleton to harden increases, but the volume of the body it must protect increases by a cube function. A giant arthropod like Arthropleura, molting its 8-foot-long body, would have faced an immense challenge. It would have had to find a perfectly safe hidden location and remain motionless for a long period, a feat that becomes harder and harder for a larger animal. The physics of molting, therefore, places a severe constraint on the maximum size an arthropod can attain. The second, and perhaps more critical constraint, is the respiratory system. As we touched upon in the previous chapter, insects and many other terrestrial arthropods do not have lungs. Instead, they breathe through a passive and decentralized network of tubes called the tracheal system. This system consists of a series of small openings on the outside of the body called spiracles, which lead to an intricate branching network of air-filled tubes, the tracheae. These tubes branch into smaller and smaller tracheoles that penetrate deep into the body's tissues, delivering oxygen directly to the cells. This is a brilliantly simple and lightweight system. It does not require a complex circulatory system or oxygen-carrying molecules like hemoglobin to transport oxygen. The air is delivered straight to where it's needed. However, this simplicity comes at a cost. It relies almost entirely on the passive diffusion of gases. Oxygen molecules must travel from the spiracles all the way down the long, narrow tubes to the cells. While this works perfectly for small organisms, it becomes incredibly inefficient as size increases. The distance the oxygen has to travel becomes too great, and the diffusion process alone cannot supply enough oxygen to meet the metabolic demands of a large, active body. This is known as the tyranny of the diffusion equation. Under the 21% oxygen levels of our modern world, this tyranny is absolute. It is the primary reason why there are no insects the size of dogs or horses today. Their respiratory system simply cannot support it. Now, let us place this unique, constrained body plan into the hyperoxygenated world of the Carboniferous. The atmospheric change did not alter the fundamental design of the exoskeleton or the tracheal system, but it dramatically changed the parameters of the engineering problem. The high oxygen concentration, up to 35%, directly addressed the respiratory constraint. The partial pressure of oxygen in the atmosphere was so high that the diffusion of oxygen through the tracheal system became far more powerful and efficient. Oxygen could be driven deeper into the body over longer distances, allowing the system to support a much larger body mass. The tyranny of the diffusion equation was temporarily overthrown. The very air was so rich that it compensated for the inherent inefficiency of the tracheal system at large sizes. This atmospheric hack allowed the insect body plan to break free from its traditional size limits and explore the realm of gigantism. The exoskeleton's constraints were also mitigated by the environment. The immense dense forests provided ample cover and hiding places for a large creature to molt in relative safety. More importantly, the high oxygen levels would have supercharged their metabolism, potentially allowing the process of hardening the new cuticle to happen more quickly, reducing the window of vulnerability. Furthermore, in the early Carboniferous, large, sophisticated vertebrate predators had not yet evolved on land. A molting Arthropleura did not have to worry about a creature like a lion or a bear stumbling upon it. Its primary threats were other arthropods, and its sheer size, even when soft, would have been a significant deterrent. Thus, the Carboniferous world created a perfect temporary alignment of conditions. It presented a world where the primary disadvantages of the arthropod body plan were neutralized, while its advantages, the protective armor, the direct respiration, were retained. It was a golden age for this ancient architecture. From a philosophical standpoint, the story of the arthropod body plan is a meditation on the relationship between form and environment. It shows that no biological design is inherently superior or inferior. Its success is entirely context-dependent. The vertebrate design, with its internal skeleton and lungs, is superbly adapted to our modern, low-oxygen world, allowing for the evolution of giants like whales and elephants. But in the specific context of the Carboniferous, the arthropod design was given a unique opportunity to produce its own, equally magnificent giants. It teaches us to see an organism not as a static object, but as a solution to a set of environmental problems. The body of a dragonfly is a solution to the problem of aerial predation. The body of a millipede is a solution to the problem of living and feeding in soil and leaf litter. For a brief period in our planet's history, the problem statement changed. The question was no longer, how can you be successful while being small? But, how large can you possibly become with this superabundant fuel? Meganeura and Arthropleura were the spectacular answers to that question. As we move forward to explore the world these creatures inhabited, we must carry with us this appreciation for their unique and elegant engineering. They were not crude, primitive monsters. They were highly sophisticated biological machines, the product of hundreds of millions of years of evolution, perfectly adapted to the world they found themselves in. They were a testament to the incredible creative potential of a body built differently, a potential that was unleashed, for a brilliant and fleeting moment, by a change in the very air they breathed. Having explored the atomic fuel and the unique biological machinery of the Carboniferous giants, we must now ascend to the scale of the environment itself. We must enter the world that cradled these creatures, a world that was both their habitat and their creator. This is the scale of the forest. The Carboniferous forest was not merely a backdrop for our story. It was the primary engine, a planet-spanning biological machine that fundamentally re-engineered the Earth's atmosphere and in doing so set the stage for the Age of Giants. To understand this era, we must walk through these ancient woods, not as a tourist, but as a planetary scientist, seeing the forest for what it truly was, a global oxygen pump and a colossal carbon sink. Let us begin by painting a picture of this alien landscape. The first thing you would notice is the silence, a deep and profound quiet unlike any forest on Earth today. There are no birds singing from the canopy, no squirrels chattering on the branches, no monkeys howling in the distance. The world of sound belongs to the whisper of the wind, the drip of water, and the faint chitinous rustle of arthropods in the undergrowth. The air is thick, warm, and heavy with humidity, carrying the rich, earthy scent of damp soil and decaying vegetation. The light is dim, filtering down through a dense, multi-layered canopy, creating a world of perpetual twilight on the forest floor. The trees themselves are strange and monolithic. They are not the familiar oaks, pines, or maples of our time. These are more ancient and primitive lineages. The true giants of this forest are the Lycopsids, or scale trees. The most famous of these, Lepidodendron, is not a true tree in the modern sense. It is a colossal club moss, a relative of the tiny humble plants that creep across forest floors today. But here, in the Carboniferous, they grew to heights of over 130 feet, 40 meters, their trunks straight and unbranching until the very top, where they split into a crown of frond-like branches. Their bark was not rough and woody, but was covered in a distinctive diamond-shaped pattern of leaf scars, giving them a reptilian, almost geometric appearance. These trees grew incredibly fast, shooting up to their full height in just a few years, and they grew in dense, tightly packed stands, creating a uniform, almost artificial-looking forest. Alongside them grew the calamites, giant horsetails. Their modern relatives are the small segmented plants you might find growing in a ditch or by a stream. But the calamites of the Carboniferous were giants, reaching heights of 60 feet, 18 meters or more. They formed dense bamboo-like thickets, their jointed, hollow stems creating another layer of the forest canopy. And weaving through all of this were the great tree ferns, their massive, intricate fronds spreading out to capture the dim light, adding to the deep shade below. This was a world without flowers. Reproduction was not carried out by pollen and seeds in the way we are familiar with. These plants reproduced through spores, releasing trillions of them into the air and water, a more ancient and less efficient method. The forest floor was not a carpet of grass, but a thick, springy mat of fallen leaves, spores, and other decaying detritus. This entire vast ecosystem was built upon water. The Carboniferous was a world of swamps. The great forests grew in and around vast, shallow, low-lying wetlands. The ground was permanently waterlogged, creating an anoxic, oxygen-poor environment in the soil and water. This single fact, the lack of oxygen in the swamps, is the key to understanding the forest's role as a planetary engine. In a modern forest, when a tree dies and falls, it is quickly set upon by a host of decomposers, primarily fungi and bacteria. These organisms are highly efficient at breaking down all parts of the tree, including its toughest component, lignin. Lignin is a complex polymer that gives wood its rigidity and strength. It is what allows trees to grow tall. As the decomposers break down the wood, they release the carbon stored within it back into the atmosphere as carbon dioxide through their own respiration. This is a key part of the Earth's natural carbon cycle. But in the Carboniferous, something was different. While plants had evolved the incredible innovation of lignin to grow tall and strong, the microbes capable of efficiently breaking it down had not yet caught up. The specific types of fungi that are the primary decomposers of lignin in our world today, the white rot fungi, had not yet evolved. This created a critical bottleneck in the carbon cycle. When the giant lepidodendron and calamites trees died, they fell into the stagnant, anoxic swamp water. Without oxygen, and without the right kind of microbes, they did not rot. The process of decomposition was incredibly slow and incomplete. Instead of being broken down and releasing their carbon, the dead trees simply piled up layer upon layer for millions of years. This created immense thick deposits of partially decomposed plant matter, which we call peat. Over geological time, as sea levels changed and these ancient swamps were buried under layers of sediment, this peat was subjected to immense pressure and heat. This geological cooking process slowly transformed the peat, driving off water and other impurities and concentrating the carbon. The result was coal. The vast coal seams that stretch across continents are the fossilized remains of these ancient undecomposed forests. Every lump of coal is a piece of a Carboniferous tree, a packet of ancient sunlight captured through photosynthesis and buried for 300 million years. This process had a dramatic and planet-altering effect on the atmosphere. The forests were acting as a colossal carbon sink. They were constantly pulling carbon dioxide out of the atmosphere through photosynthesis, but that carbon was not being returned through decomposition. It was being taken out of the system and buried underground. As carbon dioxide levels in the atmosphere plummeted, the process of photosynthesis, which produces oxygen as a byproduct, continued unabated. The result was a dramatic and sustained rise in atmospheric oxygen. The planet's atmosphere was being fundamentally re-engineered by its own biosphere. The forest was, in effect, terraforming the planet. It was this process, this failure to rot, that created the hyperoxygenated atmosphere that allowed the giant insects to exist. The giants were, in a very real sense, a byproduct of this global system of inefficient decomposition. They were living in a world made possible by what was not happening in the swamps beneath their feet. From a philosophical perspective, the Carboniferous forest is a powerful illustration of the concept of a system in disequilibrium. It was a world out of balance. The rate of production, photosynthesis, was vastly greater than the rate of consumption, decomposition. This imbalance is what drove the dramatic changes in the atmosphere and allowed for the unique evolutionary pathways of the era. It is a reminder that the most interesting and creative moments in the history of life often happen not when a system is in perfect, stable equilibrium, but when it is in a state of flux and transition. As we stand in this silent, colossal forest, we can feel the power of this green engine all around us. The thick, oxygen-rich air is a direct product of the countless leaves photosynthesizing in the canopy above. The springy ground beneath our feet is the raw material for the coal that will one day power a future, unimaginable civilization. The very existence of the giants that fly and crawl around us is tied to the microbial inefficiency in the mud below. This forest is a single, interconnected, planetary-scale machine. It is a world builder. It challenges our modern perception of a forest as a passive, scenic environment. The Carboniferous forest was an active, geological force, a biological entity that seized control of the planet's major chemical cycles and created a world in its own image. It was a calm, green and silent kingdom, but its influence was as powerful and transformative as any volcano or asteroid. It was the heart of the Carboniferous world, and its slow, steady pulse dictated the rhythm of life for an entire age. Having understood the atomic fuel, the biological machinery, and the planetary engine that defined the Carboniferous, we can now finally enter the main hall of our exhibition. This is the scale of the giants themselves. Let us imagine ourselves walking through a calm, quiet, virtual museum dedicated to the titans of this forgotten world. Each exhibit is a window into the life of a creature that once was, a testament to the spectacular results of a high-oxygen experiment. We will pause at each display, not just to marvel at the size, but to understand the life, the purpose, and the unique beauty of each of these magnificent arthropods. Exhibit A, Meganeura, the sovereign of the skies. Our first exhibit is a breathtaking sight. Suspended in the centre of the hall as if in mid-flight is a perfect life-sized recreation of Meganeura. The sheer scale is the first thing that strikes you. With a wingspan of 2.5 feet, 75 centimetres, it is larger than any flying insect alive today, rivaling a modern seagull or a hawk. Its 4 wings, 2 on each side, are vast, glassy membranes, intricately patterned with a dark network of veins, the large nerves that give the creature its name. These veins were not just for support. They were hollow tubes that were part of its respiratory and circulatory system, helping to fuel the massive flight muscles at the base of the wings. Let us look closer at the body. The long, slender abdomen is segmented and armoured, providing both flexibility and protection. At the front is the thorax, a compact powerhouse of muscle, dedicated almost entirely to driving the wings. And then there is the head. It is dominated by 2 enormous wraparound compound eyes. Each eye, composed of thousands of individual hexagonal lenses, ommatidia, would have provided Meganeura with an incredibly wide panoramic field of vision. It could see above, below, behind, and in front, all at the same time. This was the sophisticated targeting system of an apex predator. Its vision, while not as sharp in detail as our own, would have been exceptionally sensitive to motion, allowing it to detect the slightest flicker of a potential prey's wing from a great distance. Below the eyes, its mouth parts or mandibles are sharp and serrated, designed not for chewing, but for gripping and tearing. Its 6 legs are long, slender, and covered in stiff, sharp spines. These legs were not for walking. In flight they were held forward, tucked under the head, forming a spiky, inescapable, catching basket. Now let us imagine this creature in its natural environment. Meganeura was a predator of the air, a hawker that hunted on the wing. It would have patrolled the open spaces above the swamps and the clearings within the dense forests. Its flight would have been a masterful display of power and agility. Unlike modern dragonflies, which can be nimble and darting, Meganeura's flight was likely more direct and powerful, a consequence of its great size and mass. It would have been a fast, efficient flyer, capable of covering large distances in its search for food. Its hunting strategy was one of pure aerial interception. Spotting a smaller flying insect, it would have calculated a perfect intercept course, accelerating with powerful beats of its four wings. The final moments of the hunt would have been swift and brutal. It would have swooped upon its victim, ensnaring it in its spiny leg basket. The prey would then be dispatched and consumed, often mid-flight with its powerful mandibles. It was the absolute master of its domain, the top of the aerial food chain. There was nothing in the Carboniferous skies that could threaten a fully grown Meganeura. Its life, like that of its modern cousins, was a tale of two worlds. It began as a nymph, an aquatic predator in the dark, swampy waters. This nymph would have been a formidable creature in its own right, perhaps the size of a large crayfish, hunting fish and amphibians. After its aquatic phase, it would have undergone its final transformative molt, emerging from the water to become the magnificent sovereign of the skies. Its reign, and that of its griffinfly relatives, lasted for millions of years, a testament to the success of this incredible design. Exhibit B, Arthropleura, the gentle titan of the undergrowth. We move now to our second exhibit, which rests on a recreation of the Carboniferous forest floor. The scale here is even more shocking. This is Arthropleura, the largest land-dwelling invertebrate of all time. The specimen before us is over 8 feet long, 2.5 meters, and nearly 2 feet wide. Its body is flattened and composed of over 30 overlapping segments, each a broad plate of tough chitinous armor. It resembles a colossal flattened millipede or a science fiction tank. Let's examine its features. The armor plates, or tergites, are not just for defense. They are also dotted with small pores and tubercles, which may have played a role in respiration or sensory perception. Running down its sides are its countless legs. While the exact number is unknown, it likely had well over 100. These legs were not long and spindly, but short and robust, designed to provide the power and traction needed to move its immense heavy body over the complex terrain of the forest floor. The most striking fossil evidence we have of this creature is not its body, but its tracks. The exhibit displays a fossilized trackway, a wide parallel set of prints stretching across a slab of ancient sandstone. These tracks, known as diplycnites, are a ghostly and powerful reminder of this creature's existence. They allow us to reconstruct its movement, a slow, steady, wave-like crawl as it navigated the primeval landscape. For a long time, Arthropleura's immense size led scientists to believe it must have been a fearsome predator. But as we've learned, the evidence points to a much calmer existence. Its mouthparts were not the powerful, piercing jaws of a carnivore. Instead, they were weaker, designed for processing soft plant matter. Fossilized gut contents have been found containing spores from the giant ferns and lycopods. Arthropleura was a herbivore, or more likely a detritivore. It was a gentle giant. Its daily life would have been a slow, quiet search for food. It would have moved through the deep, damp leaf litter of the forest floor, a mobile armoured composting machine. It consumed the vast quantities of decaying vegetation, helping to break it down and recycle nutrients back into the ecosystem. Its role was not that of a terrifying monster, but that of a vital, stabilizing force in its environment. It was the great gardener of the Carboniferous. Its size was its primary defense. A fully grown Arthropleura would have had no natural predators. It was simply too big and too well armoured to be attacked. Its life was likely a slow and peaceful one, a cycle of feeding, growing, and molting. The process of molting would have been its only time of vulnerability. The creature would have had to shed its entire massive suit of armour, a process that must have been a monumental and risky undertaking. Arthropleura represents a completely different path to success. It was not a swift hunter, but a slow, steady and essential component of its world. It shows us that dominance does not always require aggression. Its calm, colossal presence was a defining feature of the Carboniferous undergrowth for millions of years, a testament to a form of life that was both gigantic and gentle. Exhibit C, Pulmonoscorpius, the nightmare of the swamps. Our final exhibit takes us to the water's edge, to a recreation of a dark, murky Carboniferous lagoon. Here, half submerged in the water, is a creature that truly does embody our primal fears, Pulmonoscorpius. This breathing scorpion was a predator of terrifying proportions, reaching a length of up to 70 centimeters. Its body is instantly recognizable as a scorpion, a design of ancient and enduring lethality. At the front, two large, powerful pincers, or pedipalps, are held at the ready. These were for seizing and crushing its prey. Its 8 legs are sturdy, capable of scuttling across the muddy ground or through the shallow water. But the most menacing feature is its long, segmented tail, the metasoma, which arches high over its back, tipped with a large, sharp stinger, or telson. Fossil evidence suggests this stinger was connected to a large venom gland. Unlike Arthropleura, there is no doubt about the diet of Pulmonoscorpius. It was an apex predator of the wetlands. Its prey would have included other arthropods, fish, and, crucially, the early tetrapods, our own distant amphibian-like ancestors. A creature like Proterogyrinus, a large salamander-like amphibian, would have been a potential target. Pulmonoscorpius was a bridge between two worlds, capable of hunting both in the water and on land. It would have lurked in the shallows, an ambush predator waiting for a fish to swim too close, or a thirsty amphibian to come to the water's edge. The existence of such a large venomous predator would have exerted immense evolutionary pressure on the first vertebrates venturing onto land. It was a world where leaving the water meant entering the hunting ground of these armoured nightmares. The clash between the giant arthropods and the early vertebrates was a pivotal conflict in the history of life, and for a time the arthropods had the upper hand. Pulmonoscorpius represents the darker side of the Carboniferous world. It was not a gentle giant or a majestic flyer. It was a killer, a highly efficient and successful predator that embodied the ancient and terrifying power of the arachnid lineage. Its presence in the swamps was a constant reminder that this world, for all its calm green beauty, was also a place of brutal primal competition. As we step back from this gallery of titans, we are left with a picture of a world that was diverse, complex, and filled with magnificent forms of life. These creatures were not monsters. They were the pinnacle of evolution in their time, the perfect products of a unique and unrepeatable planetary environment. They challenge our assumptions, expand our imagination, and command our respect. Their silent, fossilized remains are a testament to a time when the Earth belonged to a different kind of giant, a time when the calm cosmos produced a world ruled by the clicking, crawling, and flying dynasty of the arthropods. Our journey has taken us from the infinitesimal scale of the atom to the magnificent scale of the giants themselves. We have understood the fuel, the machinery, and the habitat of this forgotten world. Now we must zoom out further, beyond the forest, beyond the continent, until our vantage point is in the cold, silent vacuum of space, looking down upon the entire planet. From here, we can appreciate the largest and most powerful force that shaped this era, the scale of the planet itself. The story of the giant insects is not just a biological tale, it is a geological one. Their world was born from a specific configuration of the Earth's continents and climate, and it was dismantled by the slow, inexorable, and unstoppable motion of the planet's own crust. This is the story of plate tectonics, and how the dance of continents led to the end of an age. The Earth, as we know it, is a dynamic planet. Its outer shell, the lithosphere, is not a single solid piece. It is broken up into a mosaic of massive rigid plates that are constantly in motion, floating on the semi-molten mantle beneath them. This theory, known as plate tectonics, is the grand unifying theory of geology. It explains everything from earthquakes and volcanoes to the formation of mountain ranges and the shape of the continents themselves. This planetary engine, driven by the heat escaping from the Earth's core, operates on a timescale of millions of years, its movements imperceptible to a human, but transformative for the history of life. During the Carboniferous Period, this engine was in the process of undertaking one of its most significant projects, the assembly of a supercontinent. Over the preceding 100 million years, the Earth's major landmasses had been drifting towards each other. The ancient continents of Laurussia, which included much of modern-day North America and Europe, and Gondwana, which included South America, Africa, Antarctica, Australia, and India, were on a collision course. This slow-motion collision had a profound effect on the planet's geography. The closure of the ancient Reich Ocean that separated these continents created vast low-lying coastal plains and extensive inland seas. The climate of the early to mid-Carboniferous was largely defined by this geography. With so much landmass concentrated near the equator and extensive shallow seas, allowing for the circulation of warm ocean currents, the planet settled into a stable, hot, and humid greenhouse state. There were no significant polar ice caps, and the temperature gradient between the equator and the poles was much less pronounced than it is today. This global, tropical environment was the perfect breeding ground for the vast, swampy coal forests that would come to define the era. The geography of the planet was, in essence, nurturing the biological engine that would pump the atmosphere full of oxygen. However, the tectonic forces did not stop. As the Carboniferous progressed, the collision between Laurussia and Gondwana intensified. This was not a gentle docking, it was a cataclysmic crumpling of continental crust. This event, known as the Variscan orogeny, thrust up a colossal mountain range that stretched across the heart of the newly forming supercontinent, which we call Pangaea. This mountain range would have been on the scale of the modern Himalayas, a vast, impassable barrier of rock and ice. The final assembly of Pangaea and the rise of this great mountain chain marked the beginning of the end for the world of giant insects. It triggered a cascade of environmental changes, a powerful domino effect that would dismantle the Carboniferous paradise piece by piece. The first domino to fall was the climate. A single, massive supercontinent has a very different climate from a world of smaller, separate continents. The interior of Pangaea became incredibly arid. Moisture-laden winds from the vast Panthalassic Ocean that surrounded the supercontinent were blocked by the coastal mountain ranges and could not penetrate the continent's heartland. This created a vast rain shadow, leading to the formation of immense deserts in the interior. The planet's climate began to differentiate and become more extreme. The uniform, global greenhouse state gave way to a world of harsh seasonality, with brutally hot, dry summers and cold winters. The age of the swamp was coming to an end, and the age of the desert was beginning. The second domino was the collapse of the coal forests. The draining of the swamps, caused by both the mountain building and changes in global sea level, removed the habitat of the giant lycopod and horsetail trees. These ancient plants, which were so perfectly adapted to the swampy, waterlogged soil, could not survive in the new, drier, more seasonal environments. The vast, planet-spanning forests began to shrink, fragment and retreat, clinging on only in a few remaining equatorial wetlands. They were replaced by hardier, more adaptable plants like conifers and seed ferns, which were better equipped to handle the drier conditions. The third domino, and the most critical for the giant insects, was the change in the atmosphere. The collapse of the great Carboniferous forests meant the collapse of the great planetary oxygen pump. With fewer trees photosynthesizing and the end of the massive-scale carbon burial, the atmospheric oxygen levels began a long, steady decline. The process that had supercharged the atmosphere for millions of years ground to a halt and then went into reverse. From its peak of around 35%, oxygen content started to fall, eventually dropping below 20% in the subsequent Permian period. As we have explored, this was a direct and fatal blow to the giant arthropods. Their gigantism was a luxury afforded to them by a temporary atmospheric anomaly. As their fuel supply was cut off, the laws of physics and biology, which had once enabled their immense size, now became their executioner. The tracheal system could no longer support their large bodies. Their world was quite literally running out of breath. The final domino was the rise of new competitors. The new, drier world of Pangaea was a perfect stage for the evolution and diversification of the reptiles. Freed from the need to reproduce in water by the invention of the amniotic egg, reptiles were able to conquer the arid continental interiors where the amphibians could not follow. The Permian period became the age of reptiles. These new vertebrates were faster, more efficient, and in many cases larger than the struggling arthropod giants. They were the new masters of the landscape. The ecological niches once filled by the titans of the Carboniferous were now being occupied by creatures like the sail-backed Dimetrodon and the ancestors of the dinosaurs. From our vantage point in space, watching this planetary drama unfold over millions of years, we gain a profound sense of the Earth as a single integrated system. It is a system where the movement of continents in the deep mantle can determine the fate of a dragonfly in the sky. It is a system where the evolution of a new type of fungus can alter the composition of the entire atmosphere. It is a system where geology, chemistry, and biology are so deeply intertwined that they cannot be understood in isolation. The story of the planet in motion is a calming yet powerful narrative. It is a story of slow, immense, and unstoppable forces. The rise and fall of the giant insects was not a failure of life, but a natural consequence of living on a dynamic and ever-changing world. The planet gives, and the planet takes away. For a brilliant period, the specific configuration of the Earth's tectonic plates created a window of opportunity, a unique environmental niche that allowed for the evolution of some of the most magnificent creatures in the history of life. And when that window closed, as it was always destined to, that particular chapter of life's story came to its natural conclusion. The silence of the giants is, in this sense, the silence of the mountains rising and the continents moving. It is the silence of a world gracefully, if brutally, transforming itself. It is a testament to the fact that the ultimate architect of life's destiny is the planet itself, a calm, colossal, and ever-moving stage for the grand, unfolding epic of evolution. Our journey has traversed the scales of existence, from the quantum realm of the atom to the global sweep of plate tectonics. Now, we must embark on a journey across the most abstract and mind-bending scale of all, the scale of deep time. The world of the giant insects is separated from us by a gulf of 300 million years, a span of time so immense that the human mind struggles to grasp it. How then can we possibly know anything about this lost world? How can we reconstruct the shape of a Meganeura's wing, or the diet of an Arthropleura? The answer lies in a story written not in books, but in the very substance of the Earth itself. It is a story written in stone, and the science of reading that story is paleontology. This chapter is a meditation on the nature of deep time, and a tribute to the patient, detective-like work that allows us to hear the echoes of a world that has been silent for eons. Deep time is a concept that fundamentally alters our perception of reality. Our everyday experience of time is linear and fleeting, measured in seconds, hours, and years. But the Earth operates on a different clock. Its history is measured in epochs and eras, in millions and billions of years. To visualize this, imagine the entire history of the Earth, from its formation 4.5 billion years ago to the present day, compressed into a single 24-hour day. The first life would appear around 4 a.m. The world of the giant insects, the Carboniferous Period, would not begin until late in the evening, around 10:40 p.m. The entire age of dinosaurs would last for less than an hour. And the whole of recorded human history from the ancient Egyptians to the present moment would flash by in the last fraction of a second before midnight. Our existence is a mere blink in the eye of geological time. The world of the giant insects, which seems so ancient to us, was itself a relatively recent chapter in the planet's long story. To be a paleontologist is to learn to think on this scale, to see the world not as a static place, but as a dynamic, ever-changing entity, and to accept that the vast majority of its story unfolded in an almost unimaginable abyss of time before we arrived. So, how do we read this story? The pages of Earth's history book are the layers of sedimentary rock. All over the world, rivers, lakes, and oceans are constantly depositing tiny grains of sand, silt, and clay. Over millions of years, these sediments build up in layers, with the oldest at the bottom and the youngest at the top. This simple principle, known as the law of superposition, is the foundation of geology. As these layers are buried, the pressure and chemical processes turn them into solid rock, sandstone, shale, limestone. Occasionally, when an organism dies, its remains are rapidly buried in these sediments. The soft parts of the organism almost always decay, but the hard parts, the bones, teeth, shells, or, in the case of arthropods, the tough chitinous exoskeleton, can be preserved. Over millions of years, as the sediment turns to rock, groundwater rich in minerals seeps into the remains. These minerals slowly replace the original organic material, creating a perfect stone replica of the original structure. This is a fossil. A fossil is a miracle of preservation. The vast majority of organisms that have ever lived, well over 99.9%, left no trace behind. They were eaten, they decayed, or their remains were destroyed by geological processes. To become a fossil requires an incredibly unlikely series of fortunate events. This is why the fossil record is so incomplete. It is not a perfect encyclopedia of past life, but a fragmented, heavily edited manuscript with most of its pages missing. The work of a paleontologist is to find and interpret these fragments. It begins with fieldwork, often in remote, inhospitable badlands, where wind and water have eroded the overlying rock, exposing the ancient layers. The paleontologist is a detective searching for clues, their eyes trained to spot the subtle differences in colour and texture that might indicate a fossil. The discovery of a fossil is a moment of profound connection, a moment when a human hand touches a piece of a world that has been hidden for millions of years. Once a fossil is found, the painstaking work of excavation begins. The fossil and the surrounding rock or matrix are carefully removed, often in a large plaster jacket to protect them during transport back to a laboratory. There, the real work of interpretation starts. Technicians and scientists use a variety of tools, from dental picks and fine brushes to air-powered scribes and even CT scanners, to carefully remove the matrix and reveal the fossil within. This is where the science becomes an art. A paleontologist must take these stone fragments and reconstruct a living, breathing animal. How did it move? The fossilized joints and muscle scars on the bones provide clues. What did it eat? The shape of its teeth or mouth parts tells a story. Sharp, pointed teeth for tearing meat, flat, grinding surfaces for processing plants. How did it live? The context in which the fossil was found, the other fossils of plants and animals found alongside it, helps to build a picture of the entire ecosystem. The fossilized wing of a Meganeura, with its intricate vein structure, can be put into a wind tunnel or modelled on a computer to understand its aerodynamic properties. The fossilized trackway of an Arthropleura allows us to calculate its speed, its gait, and even its weight. The fossilized gut contents of a long-dead creature can give us a direct snapshot of its last meal. Every fossil is a puzzle piece. The paleontologist's job is to assemble these pieces, to fill in the gaps with knowledge from modern biology and physics, and to create a plausible and coherent picture of a lost world. The story of the discovery of the Carboniferous giants is a perfect example of this process. The first fragments of Arthropleura were found in the 19th century in the coalfields of Britain and Germany. Initially, scientists were baffled. Some thought they were the fossilized remains of a strange armoured plant. It was only through the discovery of more complete segments and the associated trackways that the true nature of the creature as a giant arthropod was revealed. Similarly, the first fossils of Meganeura were found in the coal mines of France in the 1880s. The sight of a perfectly preserved insect wing, 2.5 feet across, must have been a moment of pure, unadulterated shock and wonder for the scientists who first laid eyes on it. It was a discovery that challenged their fundamental understanding of what was possible for an insect. From a philosophical perspective, the study of deep time and the fossils it contains is a deeply calming and centering practice. It connects us to the immense, silent and patient processes of the earth. It teaches us that the world is a place of constant creation and destruction, of cycles that operate on a scale far beyond our own lives. The fossil of a Carboniferous insect is a tangible link to this immensity. It is a memento of a world that existed long before us and that will continue to exist long after we're gone. It also instills a sense of profound gratitude for the present moment. The world we inhabit, with its specific climate and biodiversity, is just as unique and temporary as the world of the Carboniferous. By understanding the worlds that have been lost, we can better appreciate the world that we have. We learn to see the dragonfly, the millipede, and the forest not as ordinary, but as the current beautiful expressions of a 4-billion-year-old story. The story written in stone is the ultimate calm narrative. It is a story without ego, without urgency, without judgment. It simply is. The rocks record the rise of the forests, the change in the air, the reign of the giants, and their eventual decline. They hold this history in a silent, patient embrace, waiting for a curious mind to come and read it. The work of paleontology is the act of listening to this silence, of translating this stone-bound story into a language we can understand, and in doing so, expanding our own sense of self to encompass the vast and wondrous history of our calm, ancient and ever-changing planet. Our journey through the scales of existence is nearly complete. We have journeyed from the heart of a star to the heart of a planet, from the microscopic world of the atom to the mind-bending abyss of deep time. We have walked with giants and witnessed the rise and fall of their forgotten world. Now, in this final chapter, we must ascend to the most human of all scales, the scale of legacy. What remains of this ancient kingdom? Does its influence still resonate in our modern world? The answer is a profound and definitive yes. The Carboniferous world is not truly gone. It is a ghost that haunts our modern machine, the machine of our civilization, the machine of our biosphere and the machine of our own consciousness. Its legacy is all around us, in the air we breathe, the ground we walk on, and the very energy that powers our lives. The most immediate and tangible legacy is biological. The Carboniferous was a pivotal moment in the evolution of life, an era of explosive innovation. The fundamental body plans of the creatures we have met, the dragonflies, the myriapods, the arachnids, were not erased, but were merely downsized and refined. The modern dragonfly, darting over a sunlit pond, is a direct descendant of the lineages that flew alongside Meganeura. It is a living echo, a smaller, more efficient vessel carrying a 300-million-year-old genetic heritage. Its mastery of flight, its predatory grace, and its alien beauty are a testament to the enduring success of a design perfected in the Carboniferous skies. When we see a millipede navigating the leaf litter, we are seeing a miniature ghost of Arthropleura, still performing its vital role as a decomposer, a humble gardener carrying on the work of its colossal ancestor. More than just individual lineages, the Carboniferous cemented the dominance of insects on this planet. The evolution of flight, which reached its first spectacular apex in this period, opened up a vast new dimension for life to conquer. The development of early forms of metamorphosis allowed insects to exploit multiple ecological niches during their lifetimes, a strategy that would later lead to their incredible diversification. Today, insects are the most successful and diverse group of animals on Earth, making up over 80% of all known animal species. Their global empire, their intricate societies, their vital roles as pollinators, decomposers, and a food source for countless other species, all have their roots in the innovations of this ancient swampy world. The quiet, persistent hum of the insect world that forms the background soundtrack of our planet is a direct legacy of the Carboniferous. The second, and perhaps most impactful legacy, is geological. As we have explored, the defining feature of the Carboniferous forests was their failure to rot. For 50 million years, the planet's biosphere was engaged in a massive one-way project of carbon sequestration. It pulled vast quantities of carbon dioxide out of the atmosphere and buried it deep underground in the form of coal. This process not only created the oxygen-rich atmosphere of the giants, but also acted as a long-term planetary thermostat, locking away a potent greenhouse gas and helping to regulate the global climate for eons to come. For hundreds of millions of years, this buried legacy lay dormant, a vast, dark treasure chest of stored energy. Then, a mere moment ago in geological time, a new species of clever primate, Homo sapiens, discovered how to open this chest. We learned to dig up this fossilized sunlight and burn it to power our machines. The Industrial Revolution, the rise of global cities, the development of modern technology, and the expansion of our population to 8 billion people, our entire modern civilization is, in a very real sense, built upon the ghost of the Carboniferous forest. We are haunted by this legacy in the most literal way imaginable. The electricity that lights this room, the screen on which these words are displayed, the transportation that moves us across continents, all are powered in large part by the silent, patient work of lycopod trees and giant ferns that lived and died 300 million years ago. This is a legacy of immense power, but also of immense danger. In the span of just 2 centuries, we have released a significant portion of this ancient sequestered carbon back into the atmosphere. We are running the film of the Carboniferous in reverse, at a terrifyingly accelerated speed. The ghost we have summoned from the machine of the Earth is now beginning to haunt the machine of our climate. The story of the Carboniferous giants, and their demise due to a changing atmosphere, has thus become a stark and urgent cautionary tale. It is a message from deep time, a warning written in stone and coal about the profound consequences of altering a planet's atmospheric balance. The final legacy is philosophical. It is the legacy that lives in our minds, in our imagination, and in our sense of wonder. The discovery of this lost world has permanently altered our understanding of our own planet. It has revealed that the Earth is not a static stage for human history, but a place of deep, almost alien, mystery and transformation. The knowledge that our world once belonged to such magnificent and strange creatures re-enchants our reality. It infuses the natural world with a sense of grandeur and deep time. This story teaches us humility. It shows us that our current world is not the goal of evolution, but simply its current state. The reign of mammals and the intelligence of humans are just one possible outcome among countless others. For a time, the planet produced a world where the pinnacle of creation was an 8-foot-long millipede, and that world was just as valid, just as real, and just as beautiful as our own. This understanding fosters a sense of kinship with all life, and a profound respect for the long, winding, and unpredictable journey of evolution. It also gives us a new lens through which to see the world. A piece of coal is no longer just a black rock. It is a fossilized piece of a giant tree, a tangible connection to a lost world. A dragonfly is no longer just an insect. It is a living relic, a ghost of a time when its ancestors ruled the skies. The story of the giants gives us a deeper, richer, and more meaningful context for the world we inhabit. As we conclude our journey, we are left with a sense of calm and profound awe. The world of the giant insects is a perfect calm cosmos story. It is a narrative that unfolds on a vast, almost silent scale. It is a story of slow, impersonal forces, the fusion in a star, the drift of a continent, the patient work of a forest, the slow breath of evolution. There are no heroes or villains, only causes and consequences. It is a story that, once heard, settles deep within the mind, a quiet and powerful reminder of the immense and beautiful complexity of our planet's history. The ghost in the machine is not something to be feared. It is something to be understood, respected, and learned from. The legacy of the Carboniferous giants is a gift of perspective. It is the gift of deep time, the gift of a deeper connection to the natural world, and the gift of a cautionary tale that may just help us to navigate our own precarious moment in the sun. The giants are silent, but their story, if we choose to listen, speaks volumes. It is the calm, deep, and resonant voice of the earth itself.